switching them from one form to the other, and also evaluating them today. On Monday, we'll talk about graphing a logarithmic equation and also finding the inverse, trying to take one and kind of change it, writing its inverse function. And then next week, we'll also look at the properties. The last goal will be to solve the equation, but we have to kind of build up to there. So we need to kind of know some properties of logs. We need to know how to evaluate logs so that we can eventually solve the equations. So the whole reason that a log was created is because we can say that 2 squared equals 4. We can say 2 cubed equals 8. But we can't say 2 to the what power equals 10. Because we don't know what that number is. I know 2 to the 4th is 16. I know 2 cubed is 8. But we don't know what the power of x would be to give us a 10. So a log was created so that we can figure that number out. And like when a lot of the math was created, I mean this was like years and years and years and years ago. This is all mathematicians did. Like they took something that frustrated them and they worked on that for their entire life, like an artist. An artist wants to do a painting, that's what they focus on like their whole day. So a math person kind of focuses on figuring something out. And then they find a pattern, and once they see that pattern, then they ask another math guy or female. At that time, it was mostly males. But then they ask somebody else, hey, I saw this pattern. Is it true? Did I find the right pattern? Can you prove that I did the right stuff? And then after they get a couple people to say, yeah, you're right, then it becomes an actual math fact that we can use. So it says, let b and y be positive numbers. B is not 1. The logarithm of y with a base of b is denoted by the following. Log base b of y. So we have log base b of y equals x. This is our conditional statement from geometry. That means either way they work. If and only if b to the x equals y. And I'm going to write it over here on the side. So if we have b to the x equals y, that's the exponential form that we've been using. It just doesn't have that initial value. So the initial value isn't sitting in front of it. Then we can change that to say log base b of y equals x. And just kind of noticing where the pieces go. So the base just drops down to the base. And then our y and x switches. So they're doing a little flip-flop. So if you're kind of lining them up vertically, you can see that the base just falls down to the base of the log. The exponent goes to the answer goes next to the log. They did a little flip-flop. It says the expression, this is going to be the weird part because you're going to start reading these. When you read them, you would say log base b of y. So I would say log base 3 of 9. That's how I would read that. Log base 3 of 9. So we're going to convert the couple problems in the chart. Just writing the exponential form. I'm going to flip my page and write them at the top here. Here we go. So exponential form, b to the x equals y. That's our exponential form that we worked with in the first 3 sections. The new log form, log base b, so the b is still there, but my x and y flip-flop, of y equals x. They flip-flop because when you find an inverse, you're switching x and y to find the inverse as well. So an inverse equation is found by switching x and y. So that's why those flip-flop as well, because I'm finding or writing its inverse. So the goal here is to convert from log form to exponential form or from exponential form to log form. And I think there are 5 examples underneath here. So just see if you can kind of take the form that it's given in, using the conversions above, try and write it in the missing form. So just see if you can try and rewrite the form, taking it from one form to the other. So we currently have log form on the left. We want to write it as exponential form on the right. All you're doing is carrying the base stays the same, flip-flopping the x and the y. first one, A, we have log base 2 of 32 equals 5. Eric, how would you write that in exponential form?
2 to the 5th equal to 32.
When you see it as an exponent, it should make sense to you. Does 2 to the 5th equal 32? Yes. If it doesn't, then you rewrote, like you changed the form incorrectly. But the exponential form better be equivalent. So if you wrote that as 5 squared equals 32, 5 squared does not equal 32. So the exponential form should make sense when you're looking at the equation. The second one gives us exponential form. So we have 1,000 equals 10 cubed. Mackenzie Myers, how would you write that as a log?
Log base 10.
Good. So log base 10, if you'd rather see this as 10 cubed equals 1,000, switch it. So here's the base. And then she said of 1,000 equals 3. So if you like seeing it flip-flop, then flip it so that the exponent's on the left. So log base 10 of 1,000 is equal to 3. Letter C, we have log base 7 of 1 equals 0. Ellie, how would you rewrite that one?
7 to the 0 power equals 1.
Does 7 to the 0 power equal 1? Yeah, any number to the 0 power is equal to 1. So the base is still 7, and then the x and the y are flip-flopping. Letter D, again, if you want to rewrite this so that the exponent is on the left, feel free to do so. That's really saying 2 to the negative 1 equals 1/2. Will, how would you write that as a log?
Log base 2 of 1/2.
Good. So log base 2 of 1/2 equals negative 1. And then the last one in the chart, log base 13 of 13 equals 1. Odette, how would you write that one?
13, the first power equals 13.
So here's the base. The base is the same. Switching the x and the y. The power of 1 gives us 13. Questions? So there are a couple examples underneath that I want you to evaluate. So your homework tonight, Matt was flipping out on me because it's 3 to 27 all. Most of those problems are just getting you to convert from one form to the other and feeling comfortable with doing that. So there's enough problems there that hopefully after you do 10 of them, maybe 12 of them, you feel comfortable and can pretty confidently just switch from one form to the other. That's all you're doing for like 12 of those problems. The other group of those problems are asking you to evaluate without using a calculator. So we're just going to see if we can try and solve for this. So we have the log base 3 of 81, and then it equals nothing. There's nothing over there, just a blank. And I'm going to place a something over there so that we can try and think of it as an equation. So for all these, I'm just going to place an x. So it at least makes it into an equation form. So rewriting again, we have b to the x equals y, or we have log base b of y equals x. And that's what all 4 of these are in. So right now, we have log base b of y equals x. So sometimes when it's in log form, it's easier to convert it to an exponent to help you solve. So Julia, if you look, we have log base 3 of 81 equals x. Can you convert that to exponential form?
It would be 3 to the x equals 81.
So here's where that common power sheet is not going to go away yet, because now we need a power of 3 that would be equal to 81. That's what the question is really saying. So 3 to what power would equal 81? That's what we're trying to solve for. Anybody know what 3 to a power would equal 81? Well, yeah, so x would be 4, because 3 to the 4th is 81. Nice job, Will. That's all you're doing there. That's how you're solving. So you're really finding that exponential value. 3 to the 4th is 81. So if you look at the next one, this one's a little more difficult. We have log base 4 of 0.25 equals x. So rewriting it, this would be 4 to the x equals 0.25. How could you change 0.25 so that it's a fraction? Julian? You would make it 1/4. Julian, how would you get an exponent to become or give you a number that's a fraction? Yeah, you'd have to use negative. So a whole number becomes a fraction with a negative exponent. So 4 to the negative 1 is equal to 1/4. So a negative exponent changes something into a fraction. If you look at letter C, we have log 1/4, 256 equals x. So the base is 1/4, and then we have 256. So if up here, my whole number became a fraction with a negative exponent, this is also going to have to be a negative exponent to make it back into a whole number. So it has to be a negative exponent. What power of 4 becomes 256? Julian? Negative 4. So 4 to the 4th is 256. 1/4 to the negative 4th is also 256. And then the last one here, we have 49 to the x equals 7. That was a little tricky. What power would you have there to give you a 7? Odette? Why 1/2? It does. So 49 to the 1/2 is the same thing as the square root of 49. Nice job, Odette. So they're a little tricky once you get those fractions. But that's all you're doing for your homework. So it really is like minimal work. Rewriting a problem. Please make sure you write the initial problem down. Anybody interested in doing 13 and 15? Mackenzie, 13, 15 together. And then Julian, 75?